Hey all dear friends, this is Prajesh Chaudhary, your Quantum Group. In this video, I'll take up a very challenging problem of rigid body dynamics that involves many concepts like kinematics of rigid body, the conservation of angular momentum, conservation of linear momentum, and that question is from INPHO 2020. So let's go ahead to solve this question. First of all, let me read the question. So this is the rod. The following is a top view of an assembly kept on a smooth horizontal table. A massless inextensible string of length d, this is an inextensible string of length d, with one end fixed while the other is attached to one end of a uniform rod of length L. The system is initially at rest with the rod aligned along the x-axis, this is the x-axis, and the string is stretched to its natural length at an angle theta with the negative y-axis, and cos theta is 1/3. At a certain instant, a bullet of the same mass m as the rod and negligible dimension is fired horizontally along the positive y direction. The bullet hits the rod at its right end with a velocity v0 and gets lodged in it, the impact being nearly instantaneous. What is the tension T in the string immediately after the impact? Assume the string doesn't break because of the sudden impulse. So the whole setup is placed on a horizontal table. The rod is like that and the string is like that, and some particle hits from here. So here is my diagram. This is a string length d, and this makes an angle theta with this line, and this is the line along which this particle is going to hit the rod perpendicularly at an end. With velocity v0, mass of the rod and the particle both are the same, and the length of the rod is L. So just after the particle, it will hit and gets lodged. Now if I take the whole system of rod and particle, and later we'll take that because they have now become just one rigid body. So the mass of this rod is m, and it's we can put the mass at the center mass, that will be at the middle of the rod, and there is this mass m. So the overall center mass of the system, here is the mass m for the rod, and there is the mass m, so that will be in between these two masses. So that will be at a distance L/4 from this end. So center mass of the whole rod plus particle system would be L/4 from here, and that would be 3L/4 from this left end. And later I need to find the moment of inertia of the whole system. So let me do that right now. So if I want to find the moment of inertia of this whole system about their center mass, so that moment of inertia would be, see, first of all, the moment of inertia of this rod about this axis, that is the center mass, so that will be mL²/12. And then using parallel axis, we have to add m into this distance square, and this distance is L/4. So mL²/12 is about this its center mass for the rod, and by using parallel axis theorem, I have to add mL/4 square. And this particle is also at a distance L/4 from the center mass. So the moment of inertia of the particle is mL/4 whole square. So overall, simplify that thing. So we'll get 5mL²/12. Now, because of this impact, this rod will get some angular velocity like that. And if we look the motion of this, and now the string get taut, so this end is fixed and the length of the string cannot be changed. The string is inextensible. So this point of the string will move in a circle like this. This is a circle. So just now because this string cannot get elongated or get slack, so it has to move along this. The velocity of this point has to be along this tangent to its length. So there's the tangent to the string at the shown moment. The velocity of this end of the string, and because that end is also connected to the rod, so in fact the velocity of this end of the rod will be along this tangent, and let me assume that that velocity is u along this direction just after impact. So that is the velocity. And we know that in rigid body, if we know the velocity of one point and angular velocity, we can find the velocity of any point of the rigid body. So I've got the direction of the velocity of this point, and I've assumed the velocity to be u. Now I want to see how the center of mass will move. So with respect to the velocity of center mass with respect to ground, let me assume this point is A. So velocity of center mass is the velocity of center mass with respect to A plus velocity of A. So with respect to this point, the center mass will have a one velocity along this direction. So that will be omega into 3L by 4. And then I have to add the velocity of that point also. So the velocity of center mass is the vector sum of 3 omega L by 4 and this u. And I've also drawn some line. So this line is basically parallel to this line, and these three lines are parallel. And this line is parallel to this line, and this line, the inclined line, is basically tangent to this string. So that's what we got. And by geometry, you can see this angle is theta. These lines are parallel, so this angle is theta, and that is a 90 minus theta, so that is theta, so this is theta. Now let's see what conservation laws we can use to get to our answer. Let's go to next page. So this is the same diagram, just I've shown here the forces. When the particle collides, there is a normal reaction between the particle and the rod, and that is internal. The weight of the particle in the rod, and there is also normal reaction from the table, and that will get cancelled. The only force acting on a rigid body system of rod and particle is the tension from the string, and obviously tension acts along the length. So if this is the net force, so we can still conserve momentum just before and just after perpendicular to the string. So this is the string, so we can conserve linear momentum perpendicular to a string, i.e. this is a perpendicular to a string, this is a perpendicular to a string. So let me draw a few more lines. This line is the along the string, and this is perpendicular to the string. So this is the initial situation, and this is the final situation. So in the final situation, we have shown the velocity of center mass, the two vectors who sum the velocity of the center mass we will get. So conservation of linear momentum perpendicular to the string. Initial linear momentum of this particle along this line, this is a theta, so that angle will be 90 minus theta. The initial linear momentum of the particle is mv0 sine theta. And after collision, the rod and the particle has become one system. So the momentum of a rigid body is the mass into its velocity of center mass. So now the total mass is 2m. So the linear momentum of this rigid body system along this line, for this part, the velocity will be 3 omega L by 4 sine theta, and this is opposite to this direction. So total linear momentum after collision would be 2m into 3 omega L by 4 sine theta minus u. That is this thing. Just simplify this thing, and just you can get m cancel, and just simplifying this thing, and we'll get you can check the calculation for the sake of getting this video short. Otherwise that will take a very long video. I've done all the calculation, but you can still check your own calculation. So we'll get this equation: 3 omega L minus 2 v naught is equal to 4u by sine theta. The variables given in the question were mass v naught, length L, d, and theta. So we have introduced two more variables, that is this omega and u. And I've got one equation connecting omega and u. I need one more equation for that to solve u and omega, and let's see what we can do more to get to solve u and omega. Already got one equation. See, now again the same diagram. Let me call this point as a, this point as a. So when the particle hits and get lodged into it, the only force acting on this rigid body system of the rod and the particle is tension, and all other force get cancelled. So can we conserve angular momentum? Yes, we can conserve angular momentum, but we can conserve angular momentum along about any point along this line, because the force, the line of action is along this line. So let me take that point as a. So we are going to conserve angular momentum about a. All other things are mentioned already. So conservation of angular momentum about a, because about a the net torque would be 0. So final angular momentum is equal to initial angular momentum. This is the final situation. Finally, the situation is some complex thing. So it is going to do CTRM. And the CTRM, the angular momentum about a point, is the angular momentum of two parts. One is the orbital angular momentum, that is mRCM cross VCM. M is the total mass, RCM is the position vector of the center mass about that point about which we want to find the angular momentum, and cross the velocity of center mass. So we are going to take, and then ICM omega, that is the spin angular momentum. So about A, this is the velocity of center mass, is the vector sum of these two parts. So if I take the component of u along the rod, that would be the u sine theta, u cos theta. So because of this component, this velocity is towards A. So because of this component, there will not be any angular momentum. So there will be angular momentum because of this component and the one component of u along this direction. So net velocity of the center mass along this direction, that will be 3 omega L by 4 minus u sine theta, and that is a perpendicular to that position vector. So the overall angular momentum orbital part would be the 2m into 3 omega L by 4 minus u sine theta into 3L by 4. So that's the L final, that is the orbital part, 2m, the mass is 2m, and the net velocity along this direction is 3 omega L by 4 minus u sine theta, and then multiply by this distance. So that is the orbiter, and that is in the dot direction like here. And omega is also in that sense, and then plus spin part, that will be the ICM omega. ICM is 5 ml square by 24 and into omega. So this is the final angular momentum. Initial angular momentum is very simple. This particle is moving like this, and about this distance is L. So initial angular momentum about A is mv naught L. mv naught L, and just simplify all those things. First get m cancel and L cancel, and simplifying all those things, we are going to get 4 omega L minus 3 V naught is equal to 9 u sine theta by 2. So now we got two equations in u and omega. Solving these two equations, we'll get the exact value of u and omega. So we've got these two equations, and the sine theta, we know sine theta, we know the theta. Cos theta is given to be 1 by 3, so that will be 2 root 2. So cos theta 1 by 3, so we would need sine theta 2 root 2 by 3. So solving these two equations and using the value of sine theta, we will get omega is equal to V naught by L and u is equal to V naught by 3 root 2. Again, you can check all these equations, solve for yourself. So we'll get these two values for omega and u. So this is once again this is right now I've shown only the rod and the particle I have not shown. This is the center of mass, which is at a distance 3L by 4. So the only force acting on this rod is the tension along the string just at the moment of collision, and because of this tension, that is the net force, and it is doing CTRM. So if I have to find the angular acceleration, so we will have to apply torque about the center mass. So if I apply torque about the center mass because of this T, so there will be one component of T here, that is a T sine theta, and this t sine theta is not going to give any torque, and this t cos theta will give a torque in this direction, and that would also be the direction of alpha. So applying I alpha is equal to torque about center mass. So ICM is equal to 5 ml square by 24, and this torque due to tension about center mass, I told you torque is because this component, that is a t cos theta, and this t cos theta is at a distance 3l by 4, so torque is t cos theta into 3l by 4, and you can use cos theta, that was given 1 by 3, and just simplify. So this 1 by 3 and 3 will get cancelled and simplify. So simplifying, we are going to get alpha is equal to 6 by 5 t by ml. So we've got alpha, we have got omega, we have got u. And also now see, we want to apply the F external is equal to MACM on the rod plus particle system. I have not shown the particle, but that is our rod plus particle system. So applying F external is equal to MACM. So we know that the net force is along the acceleration is along the net force. So acceleration of the center mass is along this direction t. So acceleration of the center mass, F external is a t, and the total mass is 2m. So ACM is equal to t by 2m. ACM is t by 2m. Now let's go to the next page. So in this diagram, what we have shown, once again, this is the center mass, this is the acceleration of the center mass. The rod has a alpha in this direction, omega in this direction. Both alpha, omega have been calculated. And let's once again see the motion of this point of the rod. The motion of this point I can tell by the string, because this is connected with the string, and this string is moving in this circle. At the moment this point has a velocity u, so it will have certainly some centripetal acceleration. It will also have tangential acceleration, but I am interested in the centripetal acceleration of this A. So mean the acceleration of A along this direction. A will also have some acceleration tangent to it, but this part, because of this length is d, so acceleration of A along a string, that would be AA would be simply u square by d. So AA along C is u square by d. And now, like we know that if we know the velocity of one point of a rigid body, we can get the velocity of any other point. Same way, if we know the acceleration of one point of a rigid body, we can get the acceleration of any point of the rigid body. So I want to show the net acceleration of this point A of this rigid body. We know the acceleration of the center mass. So acceleration of A with respect to ground is the acceleration of A with respect to center mass plus acceleration of center mass. So now with respect to center mass, the body has a both alpha and omega. So with respect to this center mass, it will have a centripetal acceleration and tangential acceleration. And then with respect to ground, I have to add that ACM. So it is rotating like this, and the rigid body, the motion of every point with respect to any other point is a circular motion. So if we look from center mass and see this point, so with respect to center mass, there will be a centripetal acceleration along this direction, and that would be 3L by 4, the distance from here to here is 3L by 4. So 3L by 4 omega square. And now the alpha is this way. So with respect to this point, there will be R alpha, like 3L by 4 alpha, one acceleration will be along this direction. And that these two, the vector sum of these two acceleration is the acceleration of A with respect to center mass. And now with respect to ground, to get the acceleration, we have to add the acceleration of center mass also. So adding acceleration of the center mass. The net acceleration of A with respect to ground is the vector sum of these three accelerations. So net acceleration of A along this direction is ACM, and Component of this along this direction would be 3L alpha by 4 cos theta. If I extend this line, so this angle would be theta, so that angle would be 90 minus theta. So component of this along this line would be 3L by 4 omega square sine theta. So net acceleration of A along this direction would be ACM plus 3L alpha by 4 cos theta minus 3L by 4 omega square sine theta, like this. Actually, this should be sine theta. Correct this. So that should be sine theta. And now we've got the main equation from where we are going to get T. And we have already got whatever we got ACM T by 2m, alpha 6 by 5 T by ml, omega V naught by L, and U is equal to V naught by 3 root 2. Just put all these four things in this equation and solve for T. So solving for T, you will get T is equal to 5m V naught square by 4, 1 by 18D plus 1 by L root 2. That is our answer. Thank you.